is a Lie group homomorphism. There's something subtle that's going on there, though, so I'm going to leave it to your later reading. My point here, what I'm trying to warn you guys about is, if you need to ever say something in your future work about Lie subgroups, you need to do some reading, because the concept of a subgroup touches on the concept of submanifold, which is a subtle one. That's it, basically. I think that was pretty much the that was pretty much it for chapter 3, and then that brings us to representation theory, which Bradley will tell us about some other day. And he gives his talk on that.
Ooh, can I make that my informational speech for Comps 101? and make you guys be my audience? Because it's online.
Really?
No, I have to give that.
That would be amazing.
I already submitted another topic.
Oh.
Several weeks ago, but that would be fun actually.
That would be fun.
I need 3 people from my audience, not just 2.
Yeah. So, a lot of the deeper results here, though, do involve the machine, which is then built in Chapter 4. Representation theory gives you... Basically, representation theory, I think, is more about... Ultimately, the representation of the algebras sort of gives you a way of sort of figuring out what are possible Lie algebras out there of a particular type. With the semi-simple Lie algebras, the ones we study. But anyway, Lie algebra, the classification of Lie algebras is pretty well thought out problem, and the theory of it by now is very pretty actually. It's beautiful. It's nicely done. Let's see here. So the next topic I was thinking that would be good for us to look at would be the problem of homogeneous spaces, right? So you guys have any questions about this, or actually, what about? I think we proved this theorem. If I remember right, I think this was in my thesis. One of the things we did was to prove this is one of Lie's theorems. I think it's Lie's third theorem. If you have a Lie group, and if you have a if you have a Lie algebra, if you have a Lie group and it has Lie algebra, and you have a sub-Lie algebra, does there exist a sub-Lie group which has that sub-Lie algebra as its Lie algebra? What I'm saying here is, with suitable definitions, yes. And if I remember correctly, that was one of the things we did over the supercategory in our own particular realm of thinking. And but anyway, that stuff's a little fuzzy for me at the moment. Mostly, I mean, the parts of it are not fuzzy. The topological refinement of what a subgroup is very fuzzy for me at the moment. It's not a big deal. I mean, we could figure it out in an hour or something, but if you don't use it, you lose it, you know? Okay, so what is a homogeneous space then? So, homogeneous spaces, one of the principal applications, so past this point in the study of Lie groups, we either need to be more careful about the foundations that we're doing in here, right, which would be the thing I would expect to see in a standard course, at least a lot of it. But then the other thing that's important, of course, is the applications of Lie groups. And the application of Lie groups to homogeneous spaces is especially pretty. This is a fairly old problem. I think this is one of the problems that really was with the study of Lie groups from the start. It's one of the things that started this all and started the study, and you know. So, I was debating whether I wanted to use Lie's book, or I brought in where did I put it?
It's 5:00 p.m.
Oh, you be quiet. Here, I just want the first definition. Actually, tell you what, I won't even do a definition, I'll just do some examples. And we'll try to make sense of them next time. How about that?
You can make up their own definition. From the example. Nice.
So one of the things this will give to us, right, is that Grassmannian example is picked up in this. For the other ball of wax, the associated fiber bundles I talked about also involve this notion. Well, not this notion per se, but the associated things about Lie groups acting on spaces. That's the thing. So he says the natural action of ON. Well, that's not to the, still not to the point. I don't want how it works. I want answers. Give me answers. I just want to write down answers. I don't want to explain to you the. There we go. That's what I was looking for. So this is, we're having our cake but not deriving it. Let's see here. The n-1 sphere can be viewed as the quotient of ON and ON-1. For example, you could look at S2 as what? O3 mod O2. Curious. And that's a diffeomorphic equals. For the action, you could also look at, oh, wait a minute. When n is greater than or equal to 2, we also have, there's more than one thing you can do. The thing that was confusing me is there's more than one thing you can do for a sphere. You also have n-1, I guess it's not too surprising, is also diffeomorphic to SO n mod SO n-1. Euclidean, this is from page 553 in Lee's smooth manifold book. Let's see here. We also have Rn, and this one's kind of exciting to me. Rn, I think this is probably my go-to example. Rn is basically equal to the Euclidean n group mod On.
What does the mod operation do to a group again?
It's like the quotient.
It's like the quotient.
Like a quotient group. So it essentially squishes everything in the subgroup to be the identity of the quotient. So it relates things, so if you have two things in En which are related by multiplication by something in On, they're considered the same point in the quotient.
So En mod On is a subgroup of En?
Yeah, En has On as a subgroup.
Okay.
En, I think, is a semi-direct product of translations and rotations.
Yeah.
So
would you just do the things that are...
it's basically Rn. I forget exactly what the notation is. It looks like there's some kind of hokey semi-direct product notation that I forget. Maybe it's that, I don't know. The point is that there is an On group in there, and when you divide by it, you're just left with kind of that piece, in some sense.
Okay. So Rn is kind of corresponding to the translations part of it.
Right, but at the same time, Rn is Rn.
Yes, it's Rn.
Yeah. And if you look at the transitive action of SL2R in the upper half plane by Mobius transformations, direct computation shows you the isotropy group of the point I. Element of U consists of matrices of the form A, B minus BA, one of my favorite kind of matrices, with A squared plus B squared equal to 1. This subgroup is exactly SO2, a subset of SL2R. Just a second here, I'll get to the point here eventually. And the characterization theorem gives us rise to diffeomorphism. U is essentially SL2R. Yeah, this is no helpful. Forget about this. This is too inside baseball for us to understand at the moment. Yeah. All right. All right. Let's see here. So S1 would be what? SO2 mod what?
So
SO1.
which is R. Yeah. Okay.
But this is a diffeomorphism you already know. Because the circle is diffeomorphic to rotations, because to each point on the circle, right, there corresponds the rotation that gets you to that point.
Why is SO2 mod SO1 still SO2?
SO1 is just one.
This is, okay. Yeah.
Yeah.
So elements correspond to themselves by multiplication by ones. Doesn't change anything. It's a stupid quotient.
That's fine.
Kind of a dumb quotient.
So S2.
So I guess the thing about this world, once we understand it properly, is it gives us a way of characterizing spaces in such a way that they're built from the same groups which act on them. So like when you're studying transformation properties of spaces, this is a very nice way of looking at things, because the spaces themselves are sets of transformations on the space. So it's all kind of intertwined. But anyway, so I will try to describe this from base principles in our next meeting, like what is a group action, and just kind of from there, if I figure. And I'm still not sure what's their best approach. I have this other, I mean, honestly speaking, this is why I toyed with the idea of using this with you guys. This is The Structure and Geometry of Lie Groups by Hilgert and Neeb. Neeb is part of an active research group that has published oodles and oodles of papers on like infinite dimensional Lie groups and all kinds of stuff. So this is written by somebody who really, really knows, or at least, there's some people who really know. Anyway, so in here, he actually has examples like Grassmannians, flag manifolds, and all kinds of other stuff. It's I'm like a moth to a flame attracted to chapter 10 in this book. Well, maybe now that I'm done with linear algebra, I'll get to it. Although it does occur to me I need to grade your stuff, huh? So if I could find it, I would grade it at this point.
We'll find more to give you.
Find more to give me? Okay, well anyway, I think that's it for today. So.